This is our lecture number 9, and we will talk about data. So in general, the course is about software design. So the data is the persistence layer where we keep the data, and usually we keep data in databases. We will discuss which databases we know, how they work in general, and how to design them and what to pay attention to. Because in most systems which you will make, you will have to make a decision about data, how to keep it, and where to keep it in the database. The structure of the lecture is this. First, we're going to discuss types of databases. There are many of them, not just one, not relational or not relational. There are many of them. I'm actually surprised to see how many. When I was preparing this lecture, I found out that there are many of them. Then we're going to discuss about, we talk about how to design on paper, how to explain to ourselves the design of the data. And then the most important question, how to choose the right database, how to make the decision which database is right for you in your particular project. And in the end, as usual, some books to recommend, maybe some conferences to publish, and then for you, call to action, what to do. So jump to the type of the databases. There are many. As usual, you can see the menu on the top, the main menu, the first line, the second menu is the next one. So you can see how many types of databases we have. I may not be accurate about how they started, I mean chronologically, which one was first, which one was next, but more or less a long time ago, they started from navigational databases. I was not even born at that time. It was, I don't know, 70 years ago. Navigational databases, the idea was that you keep the data, we keep the data somewhere in the storage, and then in order to retrieve the data, you programmers, they were supposed to write the code which you can see on the screen. Something like that. I got it from Wikipedia. I never wrote this code, but that was the idea. So you give instructions like, get me the department with the name this, and then give me the first employee in this department. And then until something go and go. So you basically go through the database in some procedural language, instructing the database how to do. So you're navigating through the database. That was the idea. So the database was like a passive element who didn't know what you're trying to do, and you are going through item to item, trying to collect information from some, I don't know what was the department, is it a table or something? I mean, I'm not an expert. For example, Integrated Data Store, that's the name of one of the first navigational databases. I don't know how many years ago. They, in most cases, most probably they don't exist anymore. Then there were hierarchical databases. Again, I got it from the book. One example is IBM Information Management System, IMS. Navigational, the idea was that we can present the information in a database in the structure, in a hierarchical structure. Something on the top, for example, electronics, and then, for example, we sell electronics, and then we sell televisions, we sell portable electronics. So probably there were some data chunks or data blocks, data maybe tables, but I'm not sure. And to get the information from there, you have to know the structure, like how they're organized, hierarchically retrieve the data from there. Again, most probably these systems don't exist anymore. And then many years ago, but still not so many years ago, relational databases showed up. Relational, probably you know about this. You've heard about it, right? So most modern databases right now, which we have, which we use, are relational. Do you know why it's relational? What's the name coming from? Why it's relational database? Because the idea behind relational database is relational calculus. So it's mathematical idea how to connect relations to relations. So each table, which you think is a table, more formally it's a relation. It's a relation from something to something. For example, you say, I have a list of names of students. So they say it's a relation because you have an ID of a student, a name of a student. So it's relation from one, they call it domain, to another domain. So one domain is IDs, another domain is names. For example, 1, 2, 3, 4, 5, 6, 7, and then Jeffrey, Anna, Peter, again Jeffrey, again Peter. So names can be duplicate, for example, but IDs are unique, and so on and so forth. The idea is that each table is a relation between domains, which are columns in more primitive way, but in more formal way, it's a relation between domains, multiple domains. Long story short, for us as programmers, we can think about that as tables. Did you have a course for databases? You did. So last year, so you forgot what it is, relations, right? No? Still remember. Oh, you forgot. Okay, so doesn't matter for you. In most cases, you can think about them as tables. In this diagram, we see tables, they are connected somehow one to another, connected through, how they are connected? Through foreign keys in most cases. Foreign keys is the best way to connect those tables. And the language. The language was presented, SQL language, SQL, which was a very interesting new principle to managing data. Instead of going to the database and retrieving the data from there, and the database just stays as a passive element, just giving you the data. In case of SQL language, the database becomes active, and you only come to the database and say, I am expecting you to give you the list of all students. And then the database starts working, it understands your request, your language, and prepares the result for you and returns to you. So they say that SQL is a declarative programming language. Probably, you remember we discussed imperative languages and declarative languages. Imperative approach is when you tell the computer what to do, explicitly saying at each step. For example, go through the list of students and retrieve me each student who is older than 15 years old. Then it goes and retrieves. In declarative, that's declarative way. An imperative way, when you go student next, take another one, compare, take and compare, take and compare. This is imperative way. So SQL was quite a bright idea for database design, and still is, because you can use SQL language to retrieve whatever you want. And this type of databases is very good when your data has a very well-defined and not frequently changing structure. I would put it this way. So I use these databases, relational databases. I use mostly Postgres, even though I give an example of Oracle, but I use Postgres. I like it most of all. Oracle is, you have to pay for it. But Postgres is free and open source. So if you use database, and I in general recommend you Postgres because it's free and open source. So I use it when I know exactly the structure of the data, and this structure is not going to change very often. For example, students in a classroom. We have a collection of students, and for each entity, we have a pretty well-defined set of fields, which is not going to change as well. So for each student, we're going to have what? The age, the name, I don't know, maybe a few other parameters, and that's it. So when this list is short, and it's the same, maybe I'm giving you the definition, which is not strict enough. So let's put it this way, that the relational database is good when, for each entity, which stays in the database, you know more or less precisely the list of attributes, and it's not going to change very often. That's the definition. If the structure is more flexible, then people very soon realize that these types of databases are not good for them. And the next step was, one of the next steps was object databases, why it's not good enough? Well, because sometimes you don't know how many attributes you have for each entity. For example, you have a data store, you design a a web shop where you sell things. But you don't sell the same thing over and over again. You don't sell mobile phones only. You sell mobile phones and books and maybe some devices, some toys, different things. And you need to keep all of this stuff in one list. So list of items you sell. But for each item, you're going to have multiple properties, multiple attributes. For mobile phones, you're going to have the price, who made the mobile phone, the size of memory, size of the screen, the year when it was made, and so on and so forth. For the book, it's going to be a completely different list of parameters. The title, the author. So how do you put in one table things like items in your store if there are books and mobile phones? You cannot make one table. You need to make a number of tables. Yeah.
What if we make another table as miscellaneous data? Then we have a column key, we have a column value, and we have an ID which refers to that particular.
That's how we did it. Yes, that's how we did it. So that's a pretty obvious proposal. So you have a list of items, the one table which is called item, where you have like books, everything, but the only one column will be the ID, yeah? Like ID. The phone, I'm selling the mobile phone, then the ID is 15. And then I'm selling the book, the ID is 16. But then I need 15 parameters for the book and 15 parameters for the mobile phone, but they're all different parameters. Then we make another table and call it parameter. And this table we say, okay, what's the item? 15. What's the parameter? Title. And what's the value of the parameter? The title of the book. Then the second line there, right? I'm explaining it correctly. The second line says, okay, the same, we again make them foreign key to here, and then we say that the attribute name is this, the value is this. That's a hybrid approach. It's okay. I mean, you can do it with a relational database, you can do whatever you want, anything you can do with a relational database. But it's not going to be elegant, it's not well elegant, because to retrieve the information from a mobile phone, you need like a join request, which in some cases may be quite heavy and quite difficult to work for the SQL database. How do you retrieve all information for mobile phone? For example, you need all attributes for the mobile phone. It's going to be join request. You select from here, joining this table. So you join two tables. It's not a big problem for a fast database, but the bigger you become, the more complex is the structure, the bigger will be the problems. I remember then how we were designing this many years ago. It is possible to do, but it's not really relational. This is not what relational databases are for. Relational databases are perfectly fit when we have a small number of attributes, well defined, like 3 attributes for this entity, 5 attributes for this, and that's that. Usually relational are very good for small data, like data with small amount of attributes and large list of them. For example, web clicks. Like they click you multiple times, many times a second. Even for this database, relationships are not perfect. But something very primitive, something which you can put into like one simple table. And for financial data, because relational databases are perfect for summarizing, for counting, for finding the maximum, finding the minimum of the table, and so forth. So if you deal with numbers, something with price, with calculation, trading, stocks, all of this, that's relational. So the next step was object databases. Object databases that was the idea and still is. They still probably on the market. I have no experience of using them. When you map the object from, say, Java directly to the database. So in Java you say, I have a book, the book has a title, set title, and boom, magically the database understands what you're doing, and inside the database the book has a title. So that's the idea. So the database kind of looks like the Java world to you.
How is it different from ORM?
How is it different from object relational mapping? In ORM, you need ORM, so you need some mechanism of understanding. You said title, change my title, and then ORM picks it up, turns this into SQL request, and makes update to the relational database. In their case, in object database, they eliminate this step. They just map objects to Java world, and you have like one single object space.
It seems like ORM is out of the SQL.
It seems like ORM, yes, it seems like ORM out of SQL, but the design in the database also is easier to do because you don't need to think how to translate my objects to tables, which is very often a problem. So how you're looking at the objects, you have book, the book has a title, and the title has a history of changes. So how do you map it to the tables? You need, okay, a table for books, a table for title, or maybe title is going to be the attribute. So how do you store the changes of this title? How they happen? There's another database, another table. So there has to be some mapping between object space, object domain, and relational domain, which is a hard problem to solve in general.
Can you explain that?
How can I explain this diagram? I have no idea what it means to, that's on the left you see relational database approach, which they show. Okay, it's a course. Like I said, the course has a topic, the teacher, the student, the time. And on the right side, we have object-oriented approach, where you have the course has attributes, and you look, when you design object database, you look at the right picture. You don't look at the left one. You don't have a table, just like we discussed. So you don't need to switch from one thinking to another. Because in relational databases, you have to. You have to switch to tables, from objects to tables and backwards, and that's a huge problem. In most cases, you're going to fail. It's going to be, you're going to lose something. By fail, you're going to lose something. When you design objects, you do very well, the right way, the objects. When you design tables, you do tables the right way. But how do you map them? It's in general a big problem because ORM cannot do it perfectly in difficult cases, in current cases. In a very simple, like for example, in this simple approach, the mapping from the course to the table course, maybe it will be possible without losing anything. But imagine a large hierarchy of objects. They all connected somehow, and then how do you map it to tables? Nobody knows. The next type of databases, you just need to know this. If you want to investigate, I suggest actually to try it out. So get one of them. They have open source object databases. Install it, try to configure, create a few objects there, try to make some requests because they have probably some of their own language for requesting, like updating, and see how it works. Next one is key value databases. A good example is Redis or Amazon DynamoDB. Any experience with Redis? Somebody? Oh, so you know what I'm talking about. Redis is quite simple. It's key value. They call it databases. I didn't know actually that they're called databases. Now I know. Key value. It's very. You can think of this like a simple table of two columns. On the left column there's a key. On the right column it's a value, and that's it. This is how Redis works. It's very good for very fast, because usually it stays in memory. Very fast operations, specifically for caching. In my understanding, Redis was designed for caching only. So let's say you're in the web system, people are coming to your website, you go to the database, retrieve some information, return it back to users. But if there are many people coming to you, like thousands every minute, then going back and forth to the database is going to be a problem for you. The database will not be able to retrieve the data so fast. So you want to cache, you want to keep the information here on the server and return immediately to the user without going to the server. For example, they come to your web page and ask for the price of the book. So in order to render your page, you need to show the book, and for the book you need the price, the author, and the title. Let's say your database is designed the way that you need to make 3 requests. 1 request for the title, 1 for the author, 1 for the price. 3 requests. Each request will take you, even if the database is super fast, it's going to be a few milliseconds. In the best case, I'm going to say 5 milliseconds. So you have 3 requests, it's 15 milliseconds. It's already too slow for a fast website. And if there will be hundreds of requests like this every second, then the database most probably will go down, will shut down. So what you do, you install Redis here, and the request comes in, you check in the Redis, you check in this very fast key value database because it's extremely fast. It's much faster than going to the database and returning it back. It's going to be microseconds. So you check in this key value database, you find the price of the book, and return immediately to the user. It's a caching layer.
What's the difference of it with a table which has key and value in?
From a normal relational database?
Yeah, it's indexed on key.
Why it's called key value databases instead of relational databases?
I mean, we can have one table and index it on.
Yeah, we can have a database. We have one table and call it key value database, right? That's your point. So why giving it a special name? Why a special name? Because no SQL, because there's no SQL here. In key value databases, you have no language for making requests. You have no ability to do joins with this table. So it's very restricted, very simplistic way of storing data, just key value. So in case of Redis, you have no ability to manipulate your data anyhow aside from insert or take. Just put it into this key value database table or retrieve back. That's all you can do. So not very complex, but very fast. That's the beauty of key value databases.
So here, every value is like a number of table. What exactly? For example, here we have in types book ID, album ID, and so on. So each book, album, and so on. How will they be? Will they be some kind of table, or what exactly?
How it's designed inside the database, or how it's? What's the question again?
Database. For example, the book has a list of attributes. How are they stored?
Oh, that's okay. Your question is how we design the data in there if we have the key value database. If you look at there are two pictures here. On the top you see Redis. At the bottom you see Amazon DynamoDB. So there are 2 different pictures. In case of Redis, it's like I said, a very primitive key value table with 2 columns only. So you cannot put anything there. So this Redis is perfect only for one purpose, when you need to cache an atomic data, which is identified by an ID. For example, the price of the book. You have the ID of the book, 1, 2, 3, 4, 5, and the price, $15. So that's the information you put there, nothing else. So you cannot put extra attributes. This is not what Redis is for. So Redis is for fast caching, key value caching. This is Redis. And it's super fast. Usually you install it on your own machine here. If in case of a web system, you have the web server where requests are coming to, and you have a database server. So you install Redis here. Redis stays far away from the database because you don't want to go. This is very important when you design systems for persistence. You don't want to go to database. You want to minimize the amount of traffic to the database. Because the more often you go to the database, The slower will be your system, the bigger will be the problem. So how you do this? Caching. That's the most popular solution, caching. You put something here, and Redis is only for this. And now to answer you the second question, so how do we use DynamoDB? Amazon DynamoDB is a different story. They also call it key value database, which I was surprised to learn, but they call it key value database, which I thought that it was a NoSQL database, but they say it's key value. How it works? It's exactly the same, but you can also put extra attributes there. In case of Redis, you cannot. In case of Amazon, you can put ID of the book, the price of the book, for example, and then goes other attributes. So you store more information there. But still, there's no SQL. You cannot retrieve information with some complex operations. You cannot join tables together. You cannot do many things. You can only look at your table as they have two keys. They say they have partition key and sort key. So partition key is always unique. The sorting key can be not unique, so it could be duplicated values. But when you retrieve the information, you always have to say, what is your ID here? And then you define how you sort. And then you may say what's going to be the partitioning key, or you may, or sorting key, or you may ignore this. In this case, you will receive everything. Long story short, for you, it's again the table with many, many, many values, unique ID here, potentially like not unique, but also the key here, and then list of attributes on the right. And what's interesting is that list of attributes can be different for each line. So it's not fixed. It's not like a strict table. It's more like these two columns are strict, they have two of them. But the tail could be different. Sometimes it could be one attribute, sometimes you can put 100 attributes, it doesn't matter. So each line, that's why I thought it was NoSQL, because we're going to discuss now how NoSQL works. In case of NoSQL, that's exactly the same. You have like a collection of a long list of something, and each something has a list of different variable list of attributes.
And does it usually access it, for example, in AWS Dynamo database in the same, like as fast as Redis, for example?
No, Redis is much faster. Redis is much faster because Redis is installed here. Amazon DynamoDB is something you access through the cloud. So you need to make a connection to Amazon server, which is far away from you, then make a request and return the data. So that will be, I don't know, 100 times slower than Redis. So Redis is extremely super fast. And Redis keeps everything in memory. I'm not sure about current versions. Maybe they enable some storage on the file. But to my knowledge, when I was using it years ago, it's in memory. So everything which stays there, it's in memory. That's why it's super fast. It doesn't go to the disk. It immediately returns everything from memory. Snapshots to the disk. There you go. So they have some ability to persist. But originally it was designed like in-memory, so-called database. There's like a class of databases which are called in-memory databases. Sorry, go ahead.
So if everything will be stored in the memory, what would be the difference if you will store the data in a JSON file and load this JSON file to the memory and access it the same way? Because also JSON, this is kind of...
Yeah, but then you're saying that instead of using this key value database, we can use just JSON file, keep it on disk, then load it to memory, and then go through JSON file and retrieve. You're going to implement Redis this way. That's exactly how Redis works. Redis is quite simple. I mean, you can make Redis in, I don't know, probably over a weekend. It's a simple piece of software. Well, it was. Now it's, of course, complex because Redis allows you to connect 2 servers, 3 servers. So in case of Redis, you can have one Redis here, one here, one here on 3 different servers. They connect through the ports, through TCP, and then you connect to this one, you say retrieve, and it goes through different servers, finds. So it's more complex system than you just explain. But key value database in memory, it's a hash map in Java. That's all. That's all you need. It's a primitive hash map. Of course, you can implement it in just 7 lines of code. But Redis is like more advanced way. You install it, you run it, it opens the port, you connect to it through TCP port, you start talking to it, so it's more sophisticated hash map. Okay, let's move on because we have more. Columnar databases. I didn't know they're called columnar, but I found out they exist. For example, ClickHouse by Yandex. Actually, it's an example Wikipedia gives. Here the idea, I am definitely not an expert, but the idea is that on the left you see raw store where we keep the products and each item, for example, the book we sell, it's a raw. and then there are many, many rows, and then you go to the database, you say, give me some books which are cheaper than $50. And the database just goes through the list and finds you books and returns you books. In case of column store, you go there and say, give me all the books, all the prices which are lower than 50, and it gives you just a column of prices. Something like that. I have no idea in details how it works, but I understand that it's good for large amount of rows, and each row has many, many, many attributes. For example, web click. So every time the web click comes to your site, you have many, many parameters of what happened on this click. Like the time, when it happened, what's the IP address, what's going to be the location of the page where it's coming, what was in the cookie, what was in the header, what was in the user account at this time, what was the previous history, what was the blah, blah, a lot of information on each click. So each web click will generate you a long collection of attributes. And you store it, if you store it in a relational database, then later you will come in and make some selections, and the database will be quite slow because it will retrieve a lot of data in order to satisfy your request, because each line is a few kilobytes or maybe megabytes of data. In case of column store, the database is optimized for that kind of data, and you can retrieve just selected column without taking everything. Something like that. You need to find it out. OLAP was the idea before this columnar databases, long time ago. It was also about something this, online analytical processing, when you put a lot of data into one storage, and they're all quite large horizontally, and then you're able to retrieve them in a vertical way faster. Yeah.
I think OLAP is about kind of law and view. So it's usually complemented with online transaction processing, where you often change some roles. And OLAP is about just writing a lot of data and not changing it later. So in analytics, you usually don't change the collected data.
That's a good comment, yeah. So they're saying that online analytical processing is for data which we don't change. We just store a lot, and then the data gets analyzed somehow with the database, but we don't update it massively, not frequently, as far as I understand. It's a gray area because, you know, we can call many things online analytical processing, but in general, that's the idea when there's a huge amount of data and we process it in some non-relational way. Next one is NoSQL or document databases. Different names, probably originally they were document databases and then they were called NoSQL. Who ever heard this name? NoSQL, NoSQL, NoSQL. So you know most probably what you're talking about. The most notable example is MongoDB. Ever had any experience with MongoDB? Oh, so you know what I'm talking about. So instead of making the structure of data strict, when we know upfront what are the attributes of each entity, we don't know this, we just allow any entity to have any possible attributes. So any entity for us, book, a mobile phone, a toy which we sell on the on the web shop, it's a document. And in the document we can have multiple attributes. Then we can, in any point of time, we can go to any document and add more attributes there. For example, we have an item which is called the mobile phone, which we sell online, and then somebody goes there and posts a comment, like, I don't like this mobile phone. So what do? We just go find this document in the database and add one more attribute. And in the attribute, we say this attribute is also a document, which inside contains the author of the comment, the text of the comment, when it was added, and so on and so forth. So it's very flexible structure of data, extremely flexible. You can do whatever you want because no restriction for you. There are no columns, no foreign keys, nothing. Just documents which are open for modification. But of course, there are problems how to retrieve this stuff, because if there is complete mess everywhere, each document has its own attributes, then in order to retrieve, there is no SQL language. There is some language which is designed by MongoDB, for example, which has some operators. You can do some transactions there. MongoDB language is improving from version to version. The latest versions are more powerful than versions before. But in general, if you ask me, you need to be very careful with the design of your documents anyway, because MongoDB can be very slow, where relational databases are very fast, and you cannot imagine how this request can be slow. MongoDB will be extremely slow in this case, and you will not understand what's going on. So it's completely two ways of thinking: relational database and NoSQL databases. But NoSQL is extremely flexible, especially if you don't know the structure of your data up front. You're just experimenting. So in this case, MongoDB is good. Another, we have XML databases, which again, I have no experience of using, but I wanted to. For a number of projects, I was thinking about using them, but they are not very mature to my knowledge, so no experience. So basically, the idea is that you store the data in XML documents, and then you manipulate with the documents through some queries, and you inject something into your documents, you retrieve something from the documents, but everything is XML, which is, in my opinion, very powerful if it would work perfectly, and if XML would be the language everybody understands easily, then this stuff would work. But this diagram, I even cannot properly explain this diagram. I was trying to find you the right diagram for XML databases, but I didn't manage to. So as far as I understand, everything is in XML, and they are probably disconnected from each other. I don't know how you can connect XML documents, but if you have a large collection of XML documents, then you can consider XML databases. And just a folder of XML files, yeah. I don't know, well, probably you can, if it's a folder of files, you cannot make one request which will fetch from all files. You will need to do it manually. You will need to open file by file, make a request there, and retrieve the data. If it's an XML database, then you can come from here and say, I want the name of the user wherever it is in those files. And the database will somehow index those files, like somehow prepare this information before you come with the request, and you will get the information. So it's like a collection of XML files with some layer on top of that, which will do some meta processing, which will know more about these files than just names of them. Because in case of a folder, you will have just names of files, and that's all you have.
Yes, it sounds like in some parts of history, it was a trend to make databases, so everyone made a new folder.
It was a trend, yeah, you're right, yeah, it was a trend. Most of these things, like object databases, XML databases, it was trend some time ago, yeah. XML databases, I remember maybe 15 years ago, it was like, wow, when XML was booming, and everybody thought that XML is a solution for everything, then XML databases, they just showed up. Just like object-oriented programming. Also, 20 years ago, everybody thought that that's the solution for everything. Object-oriented, objects are everywhere, so let's forget about relational databases and move to object databases. They were created, but we still have objects, still have relational databases. Next one, which is a very interesting thing on the market, which in my opinion kills many other persistence storages, Amazon S3. Who knows what it is? S3, Simple Storage Service. Amazon S3, in my opinion, was a revolution. This is how Amazon Cloud started. That was the first service on Amazon Cloud. That was about 20 years ago. So Amazon was a company selling books and some other things. And then Amazon, nobody knew about that. Nobody knew about Amazon. All we knew is like how much do you know about eBay today? eBay is okay, it's an auctioning site, nothing else. The same was for Amazon. So Amazon was just a book selling site. And then they decided that, I don't know who made this decision, but they decided to make this service, which probably was used by them. I'm sure that was internal service, which they created for themselves first. So they decided to make it public. And that was a boom. That was like a breakthrough. How it works? It's just an API. It's just you connect to it from your software through the API. Very simple API, just a few commands. And you do it like this. This is Java. So you say .put object, then you give the bucket name, like my bucket. Bucket is like a collection of objects, just a name. And then you provide the key name, like name my object ABC. And then you provide the content of the object, like take it from the file. So this content goes to Amazon, and Amazon stores it, keeps it for you. It's like a file in the web, file in the cloud, which has the name of your bucket, name of the object, and that's it, and the content. And you can, at any point of time, you can retrieve it back. You cannot modify it. I mean, you can only upload the new content, but you cannot edit the content there. You can only upload new one or take the existing one. That was it. Or you can delete it. But it was so convenient for storing data, like images, data. It was fast, it was cheap, extremely cheap. Like you pay some, like a fraction of cent for each operation, for each put operation, for each get operation. And many websites, many web services, many web systems started to use it for storing the data temporary. But we're not talking about relational data here, because you cannot make a selection of everything, you cannot summarize anything, you cannot store simple data there. You store some blob objects, binary large objects mostly. For example, an image or a file or information about your user or a profile of something or like whatever, many things which you don't want to keep on files. So you put it in Amazon S3. I think it's probably number one web service which Amazon is selling. I'm using it for everything. I mean, I think in every web project which I'm doing, well, in most of them, the first decision which database to select is Amazon S3 for different things. Of course, if I'm thinking about something where I need tables, then of course it's Postgres. But if I can go for S3 for some large data, big data, small data, then I go for Amazon S3. So you need to know how it works.
So here, every request will go through internet?
Yeah, it goes through internet, public internet, yeah. Every request, get put, but it's very fast.
Usually it's not necessary because you can put your service in Amazon's cloud and then it will be in data center.
Right, of course. If you host your server inside Amazon Cloud, then it will be much faster. But you can do it, for example, I host on Heroku mostly, and from Heroku, and Heroku hosts on Amazon. So Heroku, you basically get the same network, yeah.
Then why can't you, for example, store these files instead of on the local server?
On local server. Well,
The main server.
yes, the main server. The problem is that your server, well, if you store it locally in your files, then how about backups? Your server gets rebooted, then what happens? You restart the server, you lose the files. Or let's say you have two servers. And how do you make sure that in one server saves the file, another server can see that file immediately? There has to be some other place where you store it, some storage, some persistent storage. And installing Postgres, installing database, or making the file storage for it, specifically file storage, it's a lot of a hassle. Amazon S3 right there, you just give the credit card there, you connect there, they charge you like $3 a month, and that's it. And then you have 5 web servers and 1 storage for the data. Super simple.
Is it distributed, the file storage?
It is distributed. I don't know what's happening behind the scene there. Nobody knows. So all you have is the API. You have just an API, you put the information there, you retrieve back. How many servers they have, it's a question.
I think a lot of people know because actually a lot of companies provide Amazon S3-like services. And there's also self-hosted open source solutions with the same API, S3 compatible.
Yeah. You can implement yourself, that's a good comment. You can implement the same storage yourself, like S3, or you can use OpenStack. In OpenStack, it's an open source alternative of Amazon, so you can install it and you will have your own S3. But Amazon, we're going to discuss it today later, Amazon provides the guarantee of your data, so your data will not be lost. So all you do is just to put your information there, and then you know for sure that it's not lost, ever. It's extremely reliable service. So you need to know, I believe it's a new form of a database. Database for large binary objects. Of course, you're not going to use S3 to store the name of a user. This is not what S3 is for, but still some users do it. Some people do it, yes. What about security? Well, every time you connect, you authenticate through your password and login, so it's quite secure. So every connection, of course, it's not public. So each bucket, you can make public bucket, which will be visible to everybody, but usually people make private buckets. Bucket is like a collection of these objects. And objects can be hierarchical through slash. So you can say object / names, even though this slash doesn't mean much for Amazon, it's just a symbol. But through slashes, you can do searching in a more efficient way.
So the standard policy is that Amazon takes money for each query?
Yeah, Amazon charges you for each query, it charges you for traffic, it charges you for the size of object you store there, everything. But it's so small that if you put there 1,000 objects, you're going to pay like $2 a month or maybe $1 a month. So it's extremely cheap. Of course, if you store big, like gigabytes of data there and you request them every millisecond, then you're going to pay a lot. But it's still cheaper than your own solution, that's for sure. Well, I believe so. Okay, next one is graph databases. Graph databases, it's also a very interesting trend right now. People have it, and I know people who are big fans of these graph databases. Who of you know anything about? Oh, so you are those fans. So graph databases, they're like objects, entities, they're connected like graph, and you can put them like this, and then you can retrieve them as well as a graph. I mean, taking one and then going to another one, going through these nodes, through these edges, from one vertex to another one. What's the actual application of this? On this picture, we can see country, city, state, they're interconnected, and these connections are more complex than relational. So relational tables are good for quite simple connections between tables. If the connections are more sophisticated, then graph database is more suitable. And especially when you don't know upfront what's going to be the connections, then graph database is your friend. So you need to know that they exist. One example is Neo4j. It's a Java. It's I believe it's written in Java, and quite popular. The last two, and then we have a break. New SQL. New SQL, something new for me as well. It's a relational database systems that provides scalability of NoSQL. So basically they say that new SQL is it's a mix of all good things: relational, NoSQL, and transactions, ACID transactions. What is ACID? We're going to talk in half an hour. VaultDB is a notable example, which was created by the author of Postgres. So people who created Postgres, now they're working on VaultDB. And VaultDB is like a next generation, which is relational at the same time, NoSQL, and at the same time they guarantee transactions, atomicity, consistency, isolation, durability, all the good things you can meet in really like professional and mature relational databases, they have for NoSQL. I have no experience of using this stuff. I suggest you try it out. At least you know the name, New SQL. It's a trend. And the final step is big data. Big data is also very trendy now. Big word, big data, something great. Hadoop is probably the most notable example. Apache Hadoop, it's a framework which enables this big data. What is big data? Basically, the core idea of big data is that you have a large stream of data. Let's say, for example, you have financial operations coming from the server, from the trade exchange. Many transactions every second, like hundreds of transactions every second, they're coming to you. And then you want to do some analysis of the transactions. For example, you want to do some mathematical operations on this data. And you cannot do it on one machine, you cannot do it even on a large machine, so you need to somehow make it in parallel. So make sure that you have 20 machines doing some calculations in parallel. So you need to take the stream of data, parallelize it, so break it down into substreams, and then send those substreams to these machines, and then they calculate something, and then you merge the results. So basically, this is what this Hadoop is about. It's about so-called map and reduce. So they take the data you have, they map your data into chunks, like partitions, then you do something with these partitions. When the results are ready, they reduce it back to a single stream. In order to do this, they have this distributed storage, HDFS. So it is at the bottom of the picture, HDFS. It's H, I'm not sure, DFS, something distributed file system, hyper, I believe it's hyper something, hyper distributed file system, I'm not sure. So this Hadoop distributed file system, there you go. So in this distributed file system in HDFS, you can get, for example, 100 machines, connect them all to this HDFS, and then from here you just come and say, store me 1 terabyte of data, the file of 1 terabyte of data. And the system somehow automatically places this huge file into all the machines. So it distributes large, big files into multiple machines. Where are you going to use it? How are you going to use it? Only if you have really big amount of data, then you have no other option but to use something like this. So this is all about, probably you've heard this term, horizontal scalability. We're going to talk about it again in half an hour. So horizontal scalability is when you have a machine or something like a computer which is not powerful enough, and then you have two options how to make it more powerful: vertical scalability and horizontal scalability. Vertical means that you just make it bigger. It has 16 megabytes, 16 gigabytes of data, you make it 64 gigabytes of data. Not enough, you make it 256 gigabytes of data. So you make the server large, but there are certain limits. So you cannot make a server of a petabyte of data. It's just not possible, no matter how much you pay. So then you need horizontal scalability, and you keep this server the same size, but you install another 10 servers. And then in total, you have a size which you need. For example, one server has 1 terabyte of storage, but you need 100 terabytes of storage. Instead of making this server huge, you just install 100 servers. And then you need distributed file system. You need some system which will help you manage this large amount of data. This is what big data is about. How do you map and then reduce? How you map your large operation, large task, large amount of data to computational resources. And then they do the results for you, and then you reduce it back to one single result. Map reduce, that's the name, which probably is not on this diagram, but map reduce. You see distributed processing.
So how exactly can we define which databases that we use for our project?
How exactly we can define which database to use, we're going to discuss it after we talk about modeling. So that's going to be the next topic. First, we talk about this. So how do we draw the diagrams? I will basically introduce you to three methods which you can use. And we're going to talk about relational databases. So in order to explain how your tables are designed, how they connect to each other, you need to use some language. I suggest 3 languages. The first one is called IDF1X. It's a model for databases, which is each rectangle is a table or relation, and then each line is a connection. It's a foreign key where tables connect to each other. That's one graph notation to explain your colleagues what it is. The second one is UML. UML can also be used for data modeling, for relational data modeling. This is, what kind of diagram is this? Who knows? We studied which one? In UML, which diagrams do we know in UML?
Class diagram.
Class, component, deployment, sequence, activity, communication. So which one is this? It is class diagram. Yeah, it's class diagram. It's a normal class diagram. But pay attention. In each sector, in each rectangle, in a class diagram, there has to be 3 parts. The name of the class, the list of attributes, and the list of methods. Here, as you can see, the list of methods, it is present, but it's empty, always. That's how we design databases. So UML doesn't have a special notation for designing relational databases, but people use classes. People use class diagram, which is suitable, which perfectly explains what it is. For example, for each attribute, we have this, for each attribute in the table, we have this symbols plus, then we have these lines which are foreign keys. The cardinality explains the constraint on the diagram, on the database. Perfectly fine. So I would recommend you to use UML or this one. This one, entity relationship model, which existed before UML, which allows you to, not only for databases, but also for, in general, the relationship between entities, like how things are related to each other. They also have this cardinality. So each rectangle is an entity, and each diamond is a relationship. So relationship in relational database is a special table with 2 columns, probably you know about this, which represents the relationship. Yes?
How's it different from UML? Because we use the
So what's better, this one or that one? Yeah?
Yeah, so we use the R in our database course, but I, for example, don't know about UML diagram today.
Well, ER is simpler. Well, I don't know. Actually, this one is more like modern, so now everybody would understand this. This is like old-fashioned style, which is, I don't know, 30 years old. So I would suggest to stay with UML, even though UML is not very specifically for databases. So anybody can jump into this diagram, think that this is class diagram, and, for example, add an operation, a method to one of the classes. And then the everybody will be confused, like what is it? Why there's operation here if we're talking about data?
But does this diagram work for NoSQL?
Yeah, no, it's only for relational. It's only for one type of database, only relational.
And how can we define, for example, the foreign key, the primary key, and so on?
Here, for relational. So each line is a foreign key. Each line is a foreign key from one table to another. Each line is when I'm referring to another table, then this connection is a foreign key. We don't see, oh, you see the details. So take a look, for example, transaction and account.
So how do they not reach up using, for example, trans ID guy? Because it has 4 attributes, and we don't specify which one, not
Which one maps to which? Well, this relationship, they don't have names. So if you want to name these lines and make them like tables as well, you put just names on the lines. That's how I would do it. So you label your lines.
And what about the empty tables?
What about the what? Empty tables. With no attributes, just ID, just primary key. You can have 0 attributes. You have at least one, and it has to be primary key. Well, in normal relational database. So you can also make a table with 1 attribute and call it primary key, and that's it. And here, look, here we don't even know which one is primary key, which is kind of wrong, right? So maybe UML is not, well, in this diagram, well, these two, deposit and withdrawal, they don't even have primary key. So maybe this diagram is not really perfect for relational. I mean, this diagram is not well used for. Maybe this one is better. I don't know. I'm using UML. If you ask me, then I'm using UML for data design.
So you mean this diagram, this example, or the UML diagram?
No, this example is not perfect. Yeah. But UML is, in my opinion, UML is better because it's a standard for everybody, so you will not get confused if you use UML. Okay, the most interesting part of our talk, of our lecture. A number of properties of the database, how you select the database, what do you pay attention to? You can see we're going to talk about ACID, the speed, the scale, the versioning, the integrity, resilience, liability, durability. There could be many other attributes, but I decided to talk about this one. So let's start with ACID. Who knows what it is? ACID for, okay, everybody, almost. ACID is an acronym for 4 qualities, for 4 properties of a system, not only database, but usually it's applicable to databases. Atomicity, it means that when I make a request to the database, it does everything I asked or it does nothing. So it doesn't start doing something. For example, I go to the database and say, increase the salary for all employees by $5. And the database starts working, increases the salary for 5 people, and then the electricity shuts down, and other 100 people don't have the salary increase. Then we shut it, then we turn on the electricity again, the database starts, and we see that we have 5 people with increased data, with increased salary, another 100 people not increased. This is not atomicity. So that's wrong. Atomicity means I'm asking, it starts, I shut down the electricity, everything crashes, I restart, no changes there. So that's the property of the database has to be designed with this in mind, because some databases cannot guarantee that. Second one, consistency. Consistency means that if I ask the database to do something, then, and for example, in the database I know that all salaries have to be lower than $100. And then I ask the database to increase by $5. And it starts changing, and it changes, and then says, okay, I'm done, but one person gets $105. So the constraint is violated. And maybe the database says, oh, sorry, we made a mistake, but it's already updated. So the consistency, so the database turns into a non-consistent state after the update. So I asked for the update, some changes happened, but in the end, we have the database not inconsistent state, which is close to atomicity. But atomicity is about just breaking the changes at some point and not implementing the rest. This one, we implemented everything, but we turned the database into a new state which is not consistent. So database should not do that. When it starts from one state, I try to move it to another state, and if something goes wrong in this final state, if there are some violations of the rules, then the database gets back to the original state. It doesn't land into the state which is broken. Quality number 3 is isolation. So it has to be, I come from here, one connection comes from here and says, increase the salary by $5. Another connection from another computer comes at the same time and says, decrease the salary for the same person by $5. Plus 5, minus 5. What do you think should be in the end? 0, right? That means isolation. That's okay, because we implemented one change, and then after that we implemented another. Many systems will not do that. Many systems will return you plus 5, for example, after these two operations. So isolation means that no matter how many transactions come at the same time, they all will be executed consequentially. Well, like consequentially. So for us, it will look like we do it one by one. 1, 2, 3, 4, 5. So they're not going to clash. They shouldn't make changes in a way that will break the logic. For example, like I'm saying, I add plus 5, you say minus 5. Some systems will say in the end plus 5 or minus 5 or plus 10. Many things may happen if the system is not designed for isolation. If the system doesn't guarantee this I letter in the ACID. And final, durability. That means that, let's say I come to the database, I say increase the salary. The database says, okay, I increase the salary, and then I shut down the electricity the next second. Database shuts down, I turn it on, it starts, and the salary is the same before it was increased. That means there is no durability. Why it happens? It may happen to many systems, because in memory, the database usually works like this. The database has in-memory data, so when something comes in, the database just remembers and immediately tells you, okay, yes, the salary is increased, and then you're happy, you go doing something else, so transaction is very fast, and then on the background, the database starts saving this data to map to the disk. It goes to the disk because it's slow. The disk operations are very slow, so the database doesn't want to keep you waiting. So the database server says, it's done, I'm done, thank you, go ahead, like 5 milliseconds, that's it. And then it takes 50 milliseconds or maybe 1 second to find the file on the disk, to save, blah, 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 and then what happens if the answer is yours already, you walk away, and then the electricity is lost. Then my changes which were in memory, they will be lost. And when you come back to me again, it's an old salary. This is durability. And some systems are not really durable. So this ACID properties is not something that you get for free. The database has to be designed with this in mind. And when you choose the database, you ask whether ACID is supported. And very often you will get an answer, no, we don't support durability to full extent. Is isolation may work or may not. The atomicity, yes, it works, but with some exceptions. So read more details how they really support this. Very big databases. Next one, performance, is something, the speed. So you want your database to be fast. So a few things for you to remember. The first, if it's going to be relational databases, then you will definitely have questions and problems with long queries. So when you make a long SQL request, then you, especially when you join multiple tables, you will need some optimization of queries. And some databases will provide you the option for profiling. Profiling is something like you make a query to the database returns the result in 5 seconds, but you want in 5 milliseconds. So you say, okay, how about you explain to me why it was 5 seconds? For example, in Postgres, you have the instruction says explain. And then the Postgres will return you the details, like what 5 seconds were spent on. Like what exactly was done there. This is profiling. If the database provides you this, it will be easy for you to develop, and you will use this knowledge to improve your queries and maybe introduce some indexes. Second point, how you improve performance is denormalization. Denormalization, who knows what it is? Denormalization for relational databases. And you said you were learning relations. Do you know normalization? 5 forms, 5 normal forms. So denormalization is when you go back to the the normal database, you go back to a not normal. For example, in a more normal way, you have a table with users and a table with their accounts. And then you say, okay, it's too slow because I need to join them all the time. So how about I put together these two things? How about I join these two tables and I have a large table with users, accounts all together in one large table? That's denormalization, which is terrible for updates, because we'll need to update more lines every time. Updates will be slower, but selects, retrieval operations will be way faster. So denormalization is something that you may consider if the database is slow. And number 3, caching. Also, the database may allow you some caching, may enable the caching. We already discussed Redis, which you can install in front of the database. So you have a database, then you have Redis, and then you have your code. So before going to the database, you go to Redis and take from there, which is faster. But some databases may allow you caching on their own, on their side. So when you make a request to them, they, instead of running through all the data, they can immediately return you the result, which they also cache. And modern databases, I think many of them, they have caching built in. Scalability. That's a big question. We discussed that. We have horizontal and vertical scalability. We already mentioned you to this. Databases, they may support that. So some databases may allow you, well, most databases, all databases are okay with vertical scaling. They will say, okay, give me more resources, give me bigger CPUs and faster CPUs, give me more memory, give me bigger disk, I will work faster. But that's easy, like anybody can do this. Horizontal scalability is a bigger question. And they can enable a number of approaches. For example, there could be sharding or master-slave replication. Who knows what I'm talking about here? More or less, yeah? So, okay, let's start with the master-slave replication. Master-slave means that we have one large, big server who knows everything, who contains the full version of the database, and we have many, many slaves around, which also have the same database. But what happens is that in most systems, in most web systems, most applications, most operations will be retrieval operations. So if you look at any big website and see why the web front is going to the database, you will see that in most cases it goes there to retrieve the data, not to update the data, not to put something in the database. So maybe 1% of requests go for update and 99% goes for retrieval. That's why they make master-slave architecture. They make one large server, all updates go here, and then 50 slaves, usually it's like 5, 3, something like this. So one large master and small slaves. So when you want to retrieve the data, you come to them. When you want to update, you go here. So this one is the core. The master knows everything. The master has the main version of the data. And these guys, they retrieve and then give to you. So it's like a main and satellites. Satellites, they fetch the data from the master every second. Like something changes in the master, the slave fetches the data, like in a few seconds, not immediately. So when you want to update, you put to the master, and then in a few seconds, the slave has the data. If the slaves goes down, it dies, nothing is not a problem because there are 5 more slaves, everything works. If the master dies, the whole system is crashed. So usually they have 2 masters. In case of large web, for example, systems, they have 2 masters. One is the main one, another one you update here, and then you wait a little bit, so the data goes to the second master. The second master confirms and says, okay, I confirm that I also got this update, and then the transaction is finished. Then 2 changes are here, but that's slow. So you cannot have 3 masters or 4 masters. That will take a lot of time. It will be super slow to wait for each update operation when 5 masters confirm that yes, we got the data. That will be super slow. So usually there are 2 masters. They're super fast, super expensive computers. They talk to each other, any update to each of them, they exchange the data, and then large amount of slaves, which could be cheap. I mean, they don't need to be large. They don't need to be fast. They only retrieve the data from here and give the data to all the web nodes. That's the design. Sharding is something which I just explained between these 2 masters. Sharding is when you keep half of the database in one server and half of the database in another server. That's how I understand sharding. So sharding is when you break down your, probably I have the page here, yes. So sharding is when you break down your, on the left, no, maybe that's too early. So sharding is when you have a number of databases number of database servers, and each server contains only part of your data. Like in all the previous examples I gave you with master-slave. Master has everything, the full database. Another master has full database. Slaves, they have full database, like everything. In case of sharding, we have one server, it has 50% of the data. Another place has another 50% of the data. When you need the data, you need to decide which place to go. And usually there's like routers somewhere in front of these shards, and which decides which shard to redirect you to. That's another way of scaling horizontally. And then I found this picture on the internet to compare vertical scalability, scaling vertically and scaling horizontally. Maybe it's related to sharding. This page is relating to sharding. That vertical sharding is when, let's say, we have a database of 2 tables. In one table, we have a huge list of users, and another table, we have a huge list of books. So in sharding, we say, okay, on one server, we're going to have users. On another server, we're going to keep books. This is vertical sharding. And we can shard horizontally. We can say, okay, in one server, we have everything before, all records before last year. On another server, we have all users and books after last 1st of January. So we do horizontal sharding or vertical sharding. But it's still sharding. We still break down our data into shards. Shard is like a sector, like a, I don't know what the name is coming from, but sharding. This information for you so that you know that you will have to break down your database into pieces. Another point is that application layer support. So let's say the database is there, so you decide to choose this database. Ask yourself a question, is this database open source? If it's not, most probably it's not a good choice. Another, how mature is the library which you will use to connect to the database? So how old it is? Because every time you use a database, you will need some library for your programming language so that you make the connection to the database. Next question, is it a theme driver or ORM-ish framework? There are different things. A theme driver is something where you just say, this is the SQL request, send it over, return me everything which is coming from there, like in Java, JDBC. So JDBC is a theme driver. You just give instructions, SQL, it goes there, returns to the data. Or ORM-ish framework, it's more complex story. So you tell it what kind of information you want from there, and it returns you objects. Not just plain text coming from the database, but like the full structure of objects. Next one, how many languages are supported by this library? If it's a library only for Java, it's one story. If they have this database, if the database has libraries for Java, JavaScript, Ruby, Python, Go, and so on, then maybe this database is better than the one which supports only one language. And then other alternatives for the driver. So if you have only one driver with only one provider, only one developer, and if it's this company is the provider of the driver, it's no good. But if there are a number of drivers by different open source developers, then it's much better because you will always have the alternative. And believe me, most drivers, they have bugs. So you will see the problems, something will not work, and sometimes you will need to switch to alternative. If there are no alternatives, you're in trouble. Now the final question, is the API open? So if you have a database and you have a driver for the database, then the question is, how do they talk to each other? If the API is not open, only the developer of the driver knows how to talk to the database, then maybe it's not a good idea to use this database because, again, tomorrow the driver will break, you will have no other option. Another question for the databases, which I wanted to emphasize, is schema version control. That's a huge question, actually, but we will talk about this a little bit when we talk about continuous integration. But long story short, it works like this. You design your database, relational database. So you put all the tables there, you design the foreign keys, and then in a few months, you understand that you need to change something. In a few days, actually, if you develop quickly. In a few days, you decide, you know what, instead of this table, I need 2 tables. And this one, I need to increase and add some attributes. So what do? Normally, normal programmers, they just go to the database and say, update my table, alter my table, insert new column, or delete this table, make the changes directly to the database. And then tomorrow, again, the changes. Tomorrow, again, the changes. If it's a production system, somebody one day will ask you, what did you change last week that now it doesn't work? and you say, I don't remember, well, average programmers, not good programmers, but average programmers, they have some log of changes. So they will open the file and say, you know what, I'll find what I did. That was this request. And then the question will be, and Jeff, what Jeff did? I don't remember, ask Jeff. And who else has access to the database? Oh, we all have access to the database. So who did it? I've seen it many times in production systems. And they go around the office finding who did this, who deleted this table. It's not how you should work. There has to be a mechanism for versioning of it's schema version control. It's called schema version control. And the best tool, in my opinion, is Liquibase. So this is the name on the left bottom, Liquibase, in my opinion. I was using Flyway before, I was using MongoDB, I was using, MongoDB is for MongoDB, but Liquibase is for relational databases. And there's a link to one of my projects, one of my pet projects, which is connected to Postgres. And you can see, and you go by this link, and you will see the changes which I deployed to my Postgres database. So each change, when I want to change something, I don't go to the database directly. Instead, I create a file. In this file, I explain what needs to be done. For example, look, delete the table, alter table, create an index. So these are the changes. Then I put this file into repository. And then on the next continuous deployment cycle, continuous delivery cycle, the file goes to production. And Liquibase there automatically makes the changes to the schema, preserving the logs, the information, everything. So if tomorrow somebody will ask me who did the changes, who deleted the table, everything is there managed by Liquibase. So it is like Git, but for databases. Just we have Git for our files, so we don't change files just like we did 20 years ago. We have version control. 20 years ago, people were just editing files on their computers, on the floppy drives, just saving the data, and that's it. But now we have Git. So every time we change something, we preserve the log of operations. The same should happen with the database. So Liquibase, if your persistence layer is relational, then without Liquibase, you don't go anywhere. Liquibase is a mandatory tool for you. Like absolutely mandatory for all projects which are based on relational data.
I think the other way to manage that might be to use some learning framework that is called Frost. For example, Microsoft's entity framework, in which you write your data classes and you generate a schema from them. So, and actually it automatically generates files on migration. So maybe
it automatically generates file from, first it generates your schema from your Java files, for example, and then you, C#, okay, and then you change your C# files, it understands how to change the schema. Awesome, if you have such a tool, great. But I would in general recommend to stay away from automatic mapping from classes to relational. Perfect, if you have this tool, definitely use it, yeah. It's maybe even better than Liquibase for your case.
So this schema version control, it just changes the structure of the database?
It can do anything. It's a SQL request inside. You can change the data, you can change the structure, but usually it's for changing the structure, usually for modifying the tables. Add new attribute, insert new attribute for the table. You have a table, you need one extra attribute. What do? You can go to the database and run this request manually, alter table, add constraint or add attribute. You can do it manually, but this will do it automatically for you and will record, you will have the file for that, you will have the procedure for that.
So usually the SQL requests are not like that, are made with the databases are not stored somewhere in the log of this.
They are stored in the log, yeah. They're injected into the database and they go into the log. So Liquibase actually creates an extra table in the database. And in this extra table, it stores all the operations which were done. So that's how it works. So Liquibase receives the file, makes the operations, and stores it in the log.
Without this Liquibase, there's no such table. There's no.
Yes, without this Liquibase, the database will not support. I don't know any databases which would support this. So this is an extra tool on top of your database.
Why? So since this database are open source, why don't they have such a low?
That's a good question. I don't know why they don't. Well, they have log, of course. They have log, like what operations happen there. But it's much more, it will be these logs are deleted very, very soon. I mean, if it's a large database, then they have like 100, I don't know, they have millions of requests every hour. And one of those requests will be yours, coming for the changes in the schema. So how are you going to find it in the log then? The logs are, I mean, this is much more elegant way. Next one, integrity. Some databases, they support foreign keys. And foreign key is the best, well, primary key and foreign key is the best way to maintain integrity. You probably know what it is, foreign key, right? So in one table, if, for example, one table says, this is the book, and the book belongs to the student. So in the book, there's an attribute which is named student ID. And the student ID should not be able to contain whatever. We cannot put 0 there, or we cannot put there a name of the user. It has to be ID. And this ID has to be from another table. And if in this table there is no such student, then it's not possible to put the number into the book. This is what's foreign key constraint. And integrity means that if I delete the user, then something has to be done with the book. So probably book has to be deleted as well. And the database has to maintain this integrity. The database has to say, okay, you delete the user, then that's why do something with the book. Some databases don't have this primary key. For example, MySQL a long time ago didn't support that. So people were using MySQL, but always was the question, where are the foreign keys? Now, of course, they have foreign keys. But if you look back like 10 years ago, there were no foreign keys in MySQL. Another one, resilience. Resilience. I found this blog post for you because it exactly happened to me 3 years ago. MongoDB, for example, deletes the database after unclean shutdown. So MongoDB, you install it on the server, it works for half a year, you collect, it happened to me, it collects a lot of data, then something happens with the server, you shut down the server, you start again, the data is gone. Even though the data was on the disk, it was not in memory, it was on the disk. And it happened to some people as well. And then you start thinking, how can I restore this data? If you're lucky, you will restore it. I was not lucky, I lost my data. So this is resilience. Resilience is the capacity of a database infrastructure to recover from disaster and keep on providing service. Recover from disaster. I had a disaster, MongoDB did not recover from me. So I lost the data, sorry about that. So ask the database whether they provide this ability to recover. Liability. So who's going to pay for the losses? That's a good and interesting question, and I found in discussion on the internet, this is what Amazon says. Amazon says that Amazon, will not be liable to any damage, losses, blah, 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 of your data. So you put your file to Amazon S3, the file is lost, nobody is responsible. This is what Amazon says. Is it good, bad? That's what's happening right now, 2021. I just took it a few days ago from Amazon website. So they guarantee no liability. Huh?
They also guarantee that your file won't be lost.
Nobody guarantees anything, yeah. So
I don't know, it's a contradiction. Somehow they want to get the market, but they also want to be on the safer side.
I mean, I'm not complaining. I'm just saying what it is. I'm not complaining. I didn't say it's bad or good. I'm just saying this is what Amazon is saying. This is 2021. You trust your data to Amazon. Data is gone. It's your problem. So you have to think about backup, security, encryption, duplicated copies, whatever. Amazon has. I mean, it's not only Amazon. Look at Microsoft. Look at many other cloud solutions. Look at Google. They will tell you exactly the same. Why they do it, that's a different discussion. But you have to remember that your data doesn't necessarily is safe. And the last point, durability. Can we lose the data? This is what Amazon says. So Amazon S3 is designed to provide, you see how many nines? 11 nines. Durability. Durability means that if something happens to Amazon, they may lose your data. And as they say, for example, if you store 10 million objects, then on average, you expect to lose one object every 10,000 years. This is what these 11 nines mean. So pretty much, well, it's a promise, of course. I got it from their website as well. There's a link on FAQ. That's what they promise. This is called durability. So durability is measured by numbers, like availability, but durability as well. It's a very close term. That's it, I'm finishing for the data. Let me show you the books I believe you need to read. The left one is about relational databases. I believe it's a very good book, the best one about relational databases. The second one is about NoSQL. This one also interesting for those who are interested in NoSQL. Every other databases, you find books on your own. I don't know them. I read these two, so I'm suggesting you what I read. If you want to be published in the conference, then ACM Sigmod Pods conference is probably, not probably, but definitely the best. This is where people publish about databases. So if you want to say something to the world about databases, do some research, this is your place. This is top conference to publish. Call to action, if you want to do something after this course, then design relational persistence layer in your application and then make it NoSQL. So design it relational and then design it NoSQL and then compare the advantages and disadvantages. That will help you understand the differences. Because anything can be done in NoSQL and anything can be done in relational. But you will see the difference, how one is better than the others. The other, yeah.
So in the properties section, you have mentioned how we can compare databases, but you didn't mention about performance.
Performance.
For example, when I want to use like I have my project, I want to choose some database to use. Most of the parameters that you mentioned are a bit complex. For example, when I will look at SQL, I will not look, is it open source or not open source and so on. But for example, what's more important for me is the performance.
If performance is the number one objective for you, number one criteria, then pay attention to performance. But there will be other criteria which you also have to remember. But definitely, performance is one of the most important in most cases. But modern databases, they're all quite fast. If you want to select between MongoDB and Postgres, each of them is very fast. MongoDB is fast, Postgres. It depends on the data, it depends on your situation, but I would not say that some database is slow. It's just impossible to say.
There's no kind of criteria that, for example, if you have the data in, for example, if I have the data in this kind of format, it would be better to use.
Yeah, of course. For each format, you have your own choice for the database. Graph database, relational database, object database, NoSQL, document database.
Isn't that flawed is to consider before? So OLAP versus ODAP.
Yeah, it's many decisions. I cannot tell you exactly which one is better. We will need to spend another week on discussing this, like for each particular case. Maybe you can join me on the next conversation on Wednesday, and then you bring your case, and then we can discuss this case specifically, and then I can give you some recommendations. But it's every time it's case by case. Okay, and finally, the final slide. I'm sorry we're over time a few minutes. So what are the questions which still people don't have resolved, as far as I understand? The first question is how to guarantee 100% durability. So how not to lose data in MongoDB? So how can we design the system so that it shuts down and all the data which were in memory or on disk, even if we crash something, even if the file is gone, we still have the data? Big question. The second one, how to optimize database schema automatically. That's a big research direction, as far as I know right now. So you probably know that there are indexes in relational database. You know about this. And people have to manually design those indexes to create them right. Because without indexes, relational databases are super slow. They can be extremely slow, like unusable. So you need to design those indexes. The question is how to do that, and why we people have to do it manually all the time. And the bigger question, why do we need manually optimize the queries? Sometimes you design a query like very long, like I don't know how many lines, 10, 15 lines of text of SQL. And then you send this SQL to the database and it returns you the data in 25 seconds, but you want it in 25 milliseconds. So why the database cannot automatically improve the request and make it so it works faster? Now, some databases, they do something in this direction, but still we are far away from automatic optimization of queries. I believe maybe machine learning will help there, maybe some other approaches, I don't know, but that's the future. Question number 3, how to generate optimal schema automatically. We mentioned it today already, that we can take the Java code and generate schema automatically, but how can we make it right? So instead of, how can we make this mapping proper from the object world to relational world? Again, not sure we have an answer. And the final one, how to make object databases popular. I'm a big fan of object-oriented programming, and I know that object databases are not popular, so something is missing. What is missing? Why we cannot use object databases properly? I don't know. I hope that in the future we will have object databases as popular as NoSQL and as relational databases.